Hello students, let us start our today's session from hydrocarbon chapter. Aromatic compounds. The last topic of this chapter. Aroma means pleasant smelling, and these aromatic hydrocarbons are also known as arenes. Arenes is generally represented with A or H, in which the AR group is said to be aryl group, and the first member of aromatic hydrocarbon is benzene. Benzene, its formula is C6H6, in which all the 6 carbon atoms are sp2 hybridized carbon, and this 6 carbon atom that makes further bonded with 6 hydrogen atom, and all these 6 carbon atom, they have 3 alternate pi bond system. So this benzene ring, it has a planarity, and in which it has a conjugate system of diene. What do you mean by conjugate system of diene? We have to get the alternate double bond in a continuous pattern, then it is said to be a conjugate system. So benzene is also has the 3 pi bond in its structure, in its alternate position, and they can even be delocalized among all the atoms. So benzene, it is aromatic as well as a planar ring structure of conjugate diene system. And in this case, we can have the presence of the 3 pi electron that makes the high degree of unsaturation in the benzene ring. Mostly the unsaturated compounds, they will undergo addition reaction in which the unsaturation getting removed. But aromatic hydrocarbon, they do maintain their unsaturation in most of the chemical reaction. So this shows that aromatic compound does not undergo addition reaction. The benzene ring prefers to undergo substitution reactions in which the presence of pi bond maintained. And these aromatic compounds, they can further classify into benzenite, non-benzenite and polycyclic aromatic hydrocarbon. Benzenite, it should have a benzene ring. The benzene ring is made up of only the 6 carbon atom. So it is a 6-membered ring also. So benzene and its derivatives are said to be benzenite compound. What are called non-benzenite compounds? Non-benzenite compounds are the cyclic compound, in which in addition to the carbon atom, they contain the heteroatoms like oxygen, nitrogen or sulfur. Non-benzenite compounds are the one with the oxygen atom is furan, and this one is thiophene, and the one with the nitrogen NH group is pyrrole, and this is pyridine. So these are the examples of non-benzenite aromatic compound. The next one, polycyclic aromatic hydrocarbon. They are shortly represented as PAH, polycyclic aromatic hydrocarbon. In this polycyclic aromatic hydrocarbon, 2 or more benzene ring, they fuse together to give rise to the higher member of aromatic hydrocarbon. See, in this case, we have 2 benzene ring which are fused together is called naphthalene, and the other one with the 3 benzene ring fused together is anthracene, and this is the one is phenanthrene, and the one it has 9,10 dimethyl 1,2 benzoanthracene, and in this case we have 1,2,5,6 dibenzoanthracene. These polycyclic aromatic hydrocarbons are found to be carcinogenic in nature. What do you mean by carcinogenic? The matter which may cause for cancer are said to be carcinogenic. So in polycyclic aromatic hydrocarbon, when the number of ring increases, that may become highly toxic, and the ring that may go from 2 to 6 in their structure. The ring which are fusing together may find to be 2 to 6 of benzene ring. The next one, let us see about nomenclature and isomerism of aromatic hydrocarbon. Nomenclature, it's starting the first member itself benzene. So we will call it as benzene. If any substituent is there, we should find out how many substituents are there. If it has only one substituent, then we can say depends on the substituent, the name it becomes. See, this is bromobenzene as it contains benzene in its ring. So the name of the compound is bromobenzene and it is only C6H6. So the name is benzene. So when the aromatic hydrocarbon, that is the benzene ring, has more than one substituent, those are said to be disubstituted compound. If the ring it has more than two substituents in its structure, those are said to be polysubstituted aromatic compounds. So in the monosubstituted, with respect to the substituent, we can arrive its name. But when the ring has more than one substituent, then it will get the isomer of the compound. How the isomer of the compound is identified? The first substituent which is present in the ring, with respect to it, we can number the position of carbon atom. So this side it takes 1, 2, 3, 4. Similarly, we can have the opposite direction also 1, 2, 3, 4. The position 1, 2 is said to be ortho position and the position 1, 3 is said to be meta position and 1, 4 is said to be para position. So with respect to the first position, second one is said to be ortho. With respect to the first position, the third one is said to be meta and with respect to the first position, the 4 is said to be para. So in the disubstituted aromatic hydrocarbon, we can find ortho dibromobenzene, this is meta dibromobenzene, this is para dibromobenzene. And if you want to say it is in IUPAC system where we are not supposed to take ortho, para, meta. Instead, we have to say the position of halogen with numerals. So the two bromine atoms which are present in 1 and 2 position, so the name is 1, 2 dibromobenzene. And in this case, the two bromine atoms are present at 1, 3 position, so it is 1, 3 dibromobenzene. And here the bromine are at 1, 4 position, so it is said to be 1, 4 dibromobenzene. Suppose if the ring it has more than one substituent, then we have to find the base of the aromatic hydrocarbon to which we have to add the substituents and all along with their locant number. So aromatic hydrocarbon, in this we have studied about what are aromatic hydrocarbon and what about its different types of aromatic hydrocarbon and how do they name it as the nomenclature and isomerism. Now let us see about structure of benzene. That benzene, its molecular and elemental analysis that suggests the compound can have 6 carbon atom and 6 hydrogen atom, and it doesn't show any reaction with bromine water or Bayer's reagent. Bromine water, it is a reddish brown color. When alkene or alkyne reacts with it, the decolorization occurs. Similarly, alkene decolorizes the Bayer's reagent, a pink color permanganate solution, but both of the reactions not given by that benzene ring. It seems the compound it does not undergo addition reaction and hence the compound would not have a straight chain structure. And then when it reacts with ozone, ozone is O3 molecule. We know alkenes react with ozone to form carbonyl compound. Similarly, that benzene also reacts with ozone, but it forms triozonide. The formation of triozonide suggests that it has 3 pi bond in its alternate position. And moreover, it may undergo reaction with bromine. If there is unsaturation, it has to be saturated when it reacts with bromine or hydrogen or water like that. But benzene does not undergo addition reaction. Instead, it shows substitution reaction with bromine in presence of anhydrous aluminium bromide. And it forms only the mono substituted product. It doesn't form either di substituted or even poly substituted. So as it forms only mono substituted product, it suggests that all the 6 carbon atom and the hydrogen atoms are in identical manner. So 6 carbon and 6 hydrogens are present in the benzene in identical. That's why that forms only a mono substituted product. And when it undergoes the reaction with the hydrogen in presence of Raney nickel, it forms a cyclohexane. Cyclohexane is a 6-membered ring. So this suggests that benzene can have a cyclic structure, the closed ring structure, in which the double bond which may present in alternate position. So based on these evidences, Kekulé in 1865 suggested it may have a ring-like structure of cyclic planar 1. So all the 6 carbon and the 6 hydrogens are lie on a plane. And though it undergoes substitution reaction, it may give first of all mono substituted. When the mono substituted product or the reactant undergoes further reaction, it forms a di substituted product. Though it forms mono substituted or di substituted, see, there is no loss of unsaturation. The ring, it retains its unsaturation. So based on this ring, that a benzene, it may have a 6-membered ring, and in which the 3 pi bonds are present in alternate position. This is what suggested by Kekulé's structure. But as it fails to produce the addition product, Kekulé proposed that the position of 1 and 2 can have either 1 and 2 position or 1 and 2 position. It suggests that the benzene ring can be represented in 2 of the way, the one in which like this or the other one in which like this. So here we may find only the position of pi bond differ. So the property of the benzene ring that can be explained on the basis of these two structures. So benzene is composed of the structures 1 and 2. Though Kekulé proposed that planar structure, cyclic planar structure for benzene, he fails to explain about that stability, the unusual stability of the benzene molecule, and why it doesn't undergo addition reaction and it prefers to take substitution reaction. These two questions he fails to explain. So to explain about the substitution reaction and unusual stability of benzene ring, we need to know the resonance of benzene. Let us explain about the resonance and stability of benzene. The resonating structure of benzene is explained on the basis of VB theory. So in this, the pi bond is being oscillating among more than 2 atoms. See, we have the 3 pi bonds at its 1-2 position, and the same pi bond when you find here, it goes to 2-3 position. So this pi bond from 1-2 position, it changes to 2-3 position. And here the pi bond at 3-4 position is oscillating to 4-5 position. Similarly, the pi bond at 5-6 position is oscillating between 1-6 position. So the pi bond inside the ring, it gets oscillating more than 2 carbon atom. As a result of that, it takes the structure of 1 and 2. So the pi bond which are revolving inside the ring, that can be represented in a dotted circle, or we can make a solid circle inside the ring. That represents the presence of 3 pi bonds that keep on delocalizing about all the carbon atom. Let us discuss about what is the hybridization of carbon in the benzene ring. We know the benzene ring, this carbon, this carbon, this carbon. See, this is carbon-carbon double bond, and this it has carbon-carbon double bond, and 1 and 6 also carbon-carbon double bond. So all the 6 carbon atom, they have double bond. So these carbon atoms are sp2 hybridized. So when it is sp2 hybridized, that is each carbon atom, they are sharing one of its sp hybrid orbital to the adjacent carbon atom. So out of 3 sp2 hybrid orbital, 2 of them it shares between this carbon and this carbon, and one more sp2 hybrid orbital that gets overlapping with 1s1 orbital of hydrogen. Similarly, this carbon, it has 3 sp2 orbital, one of the sp2 with this carbon and other sp2 with its adjacent carbon, and the third sp2 orbital overlaps with 1s1 orbital of hydrogen. Such a way, all the 6 carbon atoms, they link through sp2 hybrid orbital. So once they form sp2 hybrid orbital, each carbon atom, they have 2p orbital. That 2p orbital that lies on perpendicular to the plane of the structure. See, all the 6 carbon atom, we have the 6 p orbital in which all of them contain 1 electron each, and the carbon-carbon that makes sigma bond, as well as carbon with hydrogen that to make sigma bond. So totally we can find there are 6 carbon-carbon sigma bond and 6 carbon-hydrogen sigma bond. Totally in a benzene ring there are 12 sigma bonds present. And let us find how the pi bonds are formed. The p orbital, which is perpendicular to the plane of each carbon atom, that may undergo sideway overlapping or parallel overlapping. So when it overlaps such a way, see that these 2 orbital that overlap, so I am getting 1 pi bond, and these 2 carbon atom that overlaps in sideway, so we have this is a pi bond, and the other 2p orbital that overlaps parallelly, that gives rise to this pi bond. So upon the overlapping of 2p orbitals of adjacent carbon atom, it may give rise to the 3 pi bond, or else they may undergo the overlapping in this way. So I am getting this double bond, and this is what the 2p orbital, and this is what 2p orbital. So this is the structure 1, this is the structure 2. So in which the position of double bond is altered. So this can be given in a combined structure. So the combination of 2 structures that can be given over here. See, this is the benzene ring I have, and in this benzene ring each carbon atom, they have the 6 2p orbital which are given just perpendicular to the plane of all the carbon atom, and the upper lobes of the p orbital that overlaps just above the plane, and lower lobes of the 2p orbital that overlaps just below the plane. So the 2p orbital of each carbon atom, after overlapping sideway or parallel, it gives rise to the plane just above the benzene ring and below the benzene ring. That makes the delocalization of pi electron among the 6 carbon atom. So the p orbital that overlaps with adjacent carbon atom, as well as the p orbital that can overlap with the next adjacent carbon atom. So all the p orbital, they have the probability of overlapping with the adjacent carbon atom equally, and moreover, as the pi orbital gets delocalized, is being strongly attracted by the nucleus of the ring. So the pi electron, if at all present between the two carbon, it will be less attracted by the nucleus. At the same time, when it is revolving around all the 6 carbon atom, then it will be strongly held by the nucleus. So that explains about stability of the benzene ring. And moreover, the X-ray diffraction studies of benzene ring, it shows that carbon-carbon bond length is 139 picometer. But this 139 picometer is just more than the carbon-carbon double bond and less than the carbon-carbon single bond. Carbon-carbon single bond that has 154 picometer and carbon-carbon double bond that has 134 picometer. But carbon-carbon bond in benzene ring is found to be 139 picometer. So the property of benzene ring that can be explained by both the structures of 1 and 2, those are said to be resonance structures or it is canonical structure. And already we have discussed about that resonance of benzene ring in the previous class itself. So benzene is a canonical form of 1 and 2 structure. So based on Kekulé structure, we are finding the 3 pi electrons that are delocalizing among the 6 carbon atom. It may give rise to 2 canonical structure and it explains about the stability of the molecule, because more the number of resonating structure, greater the stability, and the delocalization of pi electron is greatly influenced by its nucleus and hence the benzene molecule is extremely stable. Aromaticity. What do you mean by aromaticity? This is a property of conjugated cycloalkenes that makes the molecule becomes more stable due to the complete delocalization of pi electron of the system. So the criteria for aromaticity is the compound should be cyclic, a closed structure, and it must have the planar structure. Planar means all the atoms should lie on a same plane, and the compound should have a fully conjugated system. Conjugated means we have that alternate double and single bond. So in this case, each atom of the ring should have at least a p orbital, the filled p orbital, or if any heteroatom is there, it should have unshared pair of electron. And the fourth one is that must satisfy 4n plus 2 rule. So what is called 4n plus 2 rule? This n that may have the value of either 0 or any positive integer. So when n equal to 0, we will get 2 pi electron. So a closed structure, if it has 2 pi electron, then it is said to be an aromatic compound. Or when you substitute n equal to 1, that is plus 1, it becomes 6 pi electron. Or a closed structure, if it has 6 pi electron, that is said to be aromatic. So the ring structure with the conjugated doubly bond system has to satisfy the 4n plus 2 rule. This rule is said to be Huckel rule. So this is called Huckel rule. So according to this rule, we have to satisfy the 4 of these properties, and the ring must have either 2 pi electron or 6 pi electron or 10 pi electron or 14 pi electron. Besides, to calculate the number of pi electron in the ring, we can also calculate whether the given ring is aromatic or anti-aromatic or non-aromatic. Let us calculate how a ring is found to be aromatic. Let's take an example of C6H6. In this, we have the 3 pi electron in its structure. So this is the benzene ring. It has 3 pi electron. So let us count the number of pi electron in the benzene ring. It is equal to 3. Each pi electron is made up of 2 electron. So 3 into 2, it becomes equal to 6 pi electron. Let us see, according to 4n plus 2, we have 4n plus 2 that has 6 pi electron. So where we can solve the relation, we can get 4n equal to 4 or n becomes equal to 1. So n equal to 1 and it is a positive integer, This shows that the compound, it has one ring in its structure, and we can say the benzene is aromatic. Then why do we consider 4n plus 2 pi electron? According to molecular orbital theory, it explains about bonding and anti-bonding orbital. If all the shared pair of electrons are filled in bonding molecular orbital, which is at lower energy state, is found to be more stable than those have electrons in antibonding orbital with high energy. In benzene, all the 6 pi electrons, see the 3 pi electron that gets filled in their bonding molecular orbital of lower energy. That explains about the unusual stability of benzene ring. So the benzene ring is highly stable and that cannot be broken. That means it will not undergo addition reaction. This is the reason for why benzene ring does not undergo addition reaction under normal conditions. Let us take some examples for aromaticity. So I have taken benzene. It has 3 pi bond. So the total number of pi electron in the ring is 6 pi electron. And it is naphthalene. You find the 5 pi bond, that is equal to 10 pi electron. And in anthracene, there are 3 plus 2 5, 5 plus 2 7, 7 pi bonds, each bonds with the 2 electrons. So it has 14 pi electron. So according to 4n plus 2 rule, we can determine n equal to 1 for benzene, n equal to 2 for naphthalene, and n equal to 3 for anthracene. So it shows a cyclic structure with conjugate diene system, and all these pi orbital can undergo a complete delocalization. See that it can delocalize such a way, and here we can have this is delocalizes in this way. So all the conjugated pi bond should undergo complete delocalization. Here also we can find the delocalization of this is. So that confirms these compounds are aromatic. Let us take some more example from which we can identify whether it is aromatic or non-anti-aromatic or even non-aromatic. See, in this case we have a ring where we can write 4n plus 2 equal to 4 electron because of 2 pi bond. So 4n equal to 2 or n becomes equal to 2 by 4, that is equal to half. The n value, it goes fraction. So this is non-aromatic. This compound is non-aromatic. So n value must be a positive integer, but it goes a fractional, so this becomes non-aromatic. Similarly, here we can have, though the cyclobutadiene, see it undergoes a complete delocalization, even then it doesn't satisfy the 4n plus 2 pi rule, and hence it is said to be non-aromatic. Similarly, this is cyclopropene. This is cyclopropene, and this compound is cyclobutadiene. So here also we can substitute the 4n plus 2 pi rule. It has 1 pi bond, so n equal to 2, or 4n equal to 2 by 2 equal to 1, or n equal to 1 by 4. So this is also non-aromatic. Let us find thiophene. The compound is thiophene. So in this, the S, it has 2 lone pairs of electron in its 2p orbital, one from s orbital and one more from p orbital, and this pi electron that can undergo delocalization such a way. So the presence of pi orbital can undergo delocalization. Now let us consider the 4n plus 2. Here 2, 4, 6. So this is equal to 6 where n equal to 1. So this becomes aromatic compound. Similarly, here it has a pi bond system, but here these 4 carbon atoms are sp2, but this carbon is sp3. In a closed structure, all should have sp2 carbon only. So in this case, this is cyclopentadiene. It is cyclopentadiene, in which we have 2 pi bond, that is count for 4 pi electron. So when you substitute 4n plus 2 equal to 4, it becomes 4n equal to 4 minus 2 equal to 2, or n equal to 2 by 4, that is equal to 1 by 2. Once again it goes n value fractional, and it doesn't satisfy the criteria for aromaticity. Moreover, the ring, it has 4 sp2 carbon atom. Besides that, it has 1 sp3 carbon atom. So in the closed structure, all the atom should have sp2 hybridized one, or should have a negative charge, or with a positive charge, or it may have an unshared pair of electron. Such a way only we can satisfy or achieve that criteria for aromaticity. Let us take, this is cyclopropenyl anion. This is cyclo, 3 carbon atom, so this is propene, it has a negative charge, so it is propenyl. Due to negative charge, it is anion. So in the case of cyclopropenyl anion, we have 1 pi bond as well as 1 negative charge. It makes 4 electron. So for which we can identify n is equal to 4 minus 2, 2 by 4, that becomes equal to once again half. So cyclopropenyl anion is also not an aromatic compound. If we have cyclopropenyl cation, this is cyclopropenyl cation, in which we can find 4n plus 2 equal to, it has only 1 pi bond, so we can write 2, or 4n equal to 2 minus 2, or n equal to, we have 0. So n can have the values of 0, 1, 2, 3, etc. 0 or any positive integer. So for cyclopropenyl cation, n it takes the value of 0. So it is an aromatic compound, and it satisfies 4n plus 2 pi rule. So how it undergoes delocalization? This is the positive charge, it can move towards the positive charge, and hence the positive charge will delocalize at this position. Such a way it can undergo delocalization. Preparation of benzene. The first method of preparation is from coal tar. Coal tar is the residue of the fractional distillation of crude oil. When coal tar is fractionated between the temperature of 350 to 443 Kelvin, we may get the variety of benzene and its derivatives. See, benzene, toluene, xylene, naphthalene, cresol and all will be obtained at different temperatures. The next method of preparation is from acetylene. Acetylene, it is an unsaturated alkyne. When it passes through red hot iron tube at 873 Kelvin, it undergoes cyclic polymerization to form benzene. So the next method is decarboxylation. Decarboxylation, removal of carboxylic acid group, that can be done by taking soda lime. Soda lime is a mixture of sodium hydroxide and calcium oxide. So let us take sodium benzoate. This is the compound sodium benzoate. When it is heated with soda lime, it forms the sodium carbonate Na2CO3, that makes Na2CO3 plus benzene. So decarboxylation of the sodium salt of benzoic acid gives benzene. The next one from phenol. Phenol is hydroxybenzene. So we can have C6H5OH. When phenol is distilled with zinc, it gives benzene and zinc oxide. Let us see the physical properties of benzene. Benzene is highly non-polar. So they are non-polar and they immiscible or insoluble in water, and due to its aroma they behave as more repellent. The non-polar nature of the benzene that can make to dissolve in the non-polar solvents like ether, carbon tetrachloride, etc. Due to the high degree of unsaturation, they used to give sooty flame. Sooty flame means on burning it leaves some residue. Such flames are said to be sooty flame and the flame will be in yellow color. Chemical properties of benzene. So benzene, as it has 3 pi electron in its structure, that makes the molecule as electron rich center. So due to its electron rich center, it can attract the electrophiles. Electrophiles are electron seeking group. So this will undergo electrophilic substitution reaction. So in electrophilic substitution reaction, the hydrogen atom of the benzene ring can be substituted either by halogen or nitronium group or the sulfonium group or the methyl cation or the other acyl group and benzyl group. So due to the replacement of hydrogen by such groups, we will get the derivative of benzene. Let us see first of all halogenation. So the halogenation of benzene takes place when it is treated with bromine in presence of a Lewis acid like ferric bromide or aluminium bromide, where it gives rise to bromobenzene and HBr. How the reaction takes place? See, we need to have bromonium ion from the bromine molecule. So the presence of Lewis acid FeBr3 that reacts with Br2, that means it is an electron deficient compound. It can attract one of the Br towards itself, so it forms FeBr4 minus and Br plus ion. This is what the bromonium ion, the electrophile. This electrophile which can attract the benzene ring. So Br plus, this can attract the pi electron, attract the benzene ring. So we are getting an intermediate of this one. Further it undergoes resonance stabilization. Following that, the hydrogen it goes inside, we are getting bromobenzene. The H plus formed that combines with FeBr4 minus gives FeBr3 plus HBr. This is what the mechanism of the reaction. It is not necessary to explain about the resonating structure of all those. We have to say how the hydrogen is substituted by the bromonium group. So in nitration reaction, we have to take concentrated nitric acid and concentrated sulfuric acid. The sulfuric acid is necessary to produce nitronium ion from the nitric acid. This nitronium ion that reacts with the benzene ring, so plus NO2 plus. So nitrogen only carry the positive charge. So this abstract the electrophile, we are getting hydrogen and NO2. Further it will be stabilized by resonance, and finally that electron of hydrogen get into the ring, so we will get nitrobenzene. The next reaction is sulfonation reaction, in which we have to take oleum. Oleum is when SO3 is passed through sulfuric acid, that makes very strong acid of H2S2O7, that is called oleum. So when benzene is treated with the oleum, the SO3H group of sulfuric acid is replaced by the hydrogen atom of benzene ring. So the OH that attracts that hydrogen, that is left as water. So where the hydrogen is substituted by SO3H group, this is said to be benzene sulfonic acid. And the next one, Frieldel-Craft's alkylation, acylation, benzylation. All these reaction that it takes place only in presence of anhydrous aluminium chloride. Anhydrous aluminium chloride is a Lewis acid which is used to generate whether the methyl cation or acyl cation or benzoyl cation. Let us take Frieldel-Craft's alkylation. Benzene that reacts with chloromethane in presence of anhydrous aluminium chloride, it gives toluene. This methyl cation that attacks the benzene ring, it forms the intermediate of this one, followed by the reaction with the AlCl4 minus, it gives toluene, AlCl3 and HCl. Similarly, same reaction that can take place with acylation. Acyl group is nothing but RCO group is called acyl and benzyl group is ARCO group is called benzyl group. So let us see acylation. Frieldel-Craft acylation, benzylation. Acylation, we need to take acetyl chloride or its IUPAC name is ethanoyl chloride, formula CH3COCl, and benzyl chloride is C6H5COCl. Both of them are the acid derivative, the derivative of carboxylic acid. Let us take benzene with the acetyl chloride or with the benzyl chloride. The hydrogen atom of the benzene ring that takes chlorine, where the carbon, the CO group that attacks the benzene ring. So as a result of it, we will get acetophenone or benzophenone. How does that acyl cation or aryl cation, that is benzoyl cation, is produced? Just like in alkylation, we have to take that Lewis acid which react with either acetyl chloride or benzoyl chloride. It forms AlCl4 minus with the acyl cation or benzoyl cation. The positive charge should be on the carbon atom, not on oxygen, where the atom that binds with the ring should get the positive charge. See, the ring, it directly bonded with the carbon atom of acyl group. So the positive charge should be lying on the carbon atom of the resulting acid halide. Addition reactions. Benzene undergoes addition reaction with hydrogen and halogen. So when benzene is heated with hydrogen in presence of nickel or platinum catalyst, where the unsaturation of benzene ring is removed and it gets converted into cyclohexane. Similarly, when benzene is heated with chlorine at 500 Kelvin in presence of UV light, all the 6 that CH groups are converted into CHCl group. So all the 3 pi bonds are replaced by the 6 chlorine atom. So we are getting benzene hexachloride. This is known as BHC. And when benzene is on combustion in oxygen, that results in combustion reaction. When benzene is heated in oxygen, it undergoes combustion to form carbon dioxide and water. As the ring, it has 6 carbon atom, there will be 6 molecules of carbon dioxide, it has 6 hydrogen, so 3 moles of water. When you count the number of oxygen, that becomes 15, so the 15 is divided by the atomicity of oxygen, so we are writing 15 by 2 of oxygen. Further to these reactions, we may find 2 more reactions for benzene. One is vapor phase oxidation and the other one is Birch reduction. In vapor phase oxidation, benzene is oxidized to maleic acid in presence of vanadium pentoxide at 773 Kelvin. This maleic acid is an unsaturated acid. Further, this maleic acid on heating, there is a loss of water molecule between the 2 carboxylic acid. It gives rise to the compound known as maleic anhydride. So anhydride means without water. There will be a loss of water molecule between the 2 carboxylic group. As a result of that, we will get anhydride. The next one, Birch reduction, in which the benzene is converted into 1,4 cyclohexadiene. This is first carbon where the double bond is present 1, 2, 3, 4, 5, 6. So at the first position and the fourth position we have a double bond. So this is cyclohexane and it has 2 double bond. So it is called 1,4 cyclohexadiene. This is formed when benzene is treated with either sodium or lithium in liquid ammonia, that is a reducing agent, followed by treatment with alcohol. It gives 1,4 cyclohexadiene. So that's all the chemical properties of benzene. So in which it undergoes certain mechanisms for nitration, halogenation and Frieldel-Craft alkylation. These are the electrophiles which are generated during the electrophilic substitution reactions of benzene ring. So how electrophiles are generated? That is possible only in presence of some other catalyst. See, in Frieldel-Craft's reaction, we are taking anhydrous aluminium chloride as a catalyst. This is a Lewis acid, that means electron deficient compound. It is seeking of a pair of electron. So when it is in the reaction with the methyl chloride or acid chloride or benzyl chloride, the chlorine of alkyl or acyl halide can easily be attracted by the Lewis acid and hence that makes the compound of AlCl4 minus. As the result of this, the carbon halogen bond it gets broken. So carbon, as it loses the chlorine to aluminium chloride, it takes the positive charge. So we will get methyl cation or acyl cation or a benzoyl cation. So these are the electrophile which are produced during the reaction of Frieldel-Craft's reaction. And in the case of nitration, I said sulfuric acid and concentrated nitric acid, that makes nitrating mixture. In the absence of sulfuric acid, the nitric acid unable to produce nitronium ion. So how nitronium ion is formed? Sulfuric acid we can write HOSO2OH. Already I have given how the sulfuric acid structure can be represented. So this nitric acid, the OH of nitric acid can attract the proton of sulfuric acid where it forms protonated nitric acid because it has one proton excess. This is called protonated nitric acid and the bisulfate ion is produced. And the oxygen would never be stable with the positive charge. So this oxygen that withdraws the electron from nitrogen and hence it forms water and nitronium ion. Similarly, in halogenation reaction, we are taking some Lewis acid that breaks the halogen into FeCl4 minus and chloronium ion. If you have bromine, it will be bromonium ion and FeBr4 minus. So in such way, the electrophiles are produced for the electrophilic substitution reaction of benzene ring, followed by the formation of electrophile. How the electrophile that attacks the benzene ring and the arenium ion is formed. Further, the formed arenium ion is stabilized by resonance. Let us explain about. See, the benzene ring, when it attacks the electrophile, the electron that moves from 1 to carbon. So as this carbon that loses the electron, so it gets a positive charge. Here the carbon is sp2 where this carbon is into sp3. Now this positive charge is being delocalized due to the attract of pi electron towards the one. See, here I have a positive charge. This is being attracted by its adjacent, that one alternate conjugate pi bond we can say. So this attracts. So as the pi bond moves towards this carbon, now it gets the positive charge. Similarly, this pi bond, that conjugate pi bond that attracts towards the positive charge where this carbon it gets the positive charge. So the position of positive charge that moves from alternate position from this carbon to, suppose if it is first carbon, second carbon to fifth carbon. So let us consider this is the first carbon, this is the second carbon and third, 4, 5, 6. So 1, 2, 3, 4. So the position of the positive charge at second carbon goes to now fourth carbon. Now it goes to sixth carbon. Later on we can find this is the resonating structure due to the delocalization of pi electron. So the delocalization of pi electron that can be given in a dotted circle in which the ring carries the positive charge, that is what represented at its center. This is called rhenium ion. So as a result of the formation of rhenium ion, from which we have to remove the proton, that is possible by treating with the AlCl4 minus as in the case of either Frieldel-Craft reaction or halogenation reaction, or the proton to be removed by bisulfate ion if at all in the case of nitration. So let us take AlCl4 minus that can be attracted. This AlCl4 minus attracts this proton and hence the bond it comes inside. So we are having the substituted benzene. And in this AlCl4 minus plus H, that makes aluminum chloride and HCl. Similarly, if we have bisulfate ion, this bisulfate ion will attract this proton and it gets converted into sulfuric acid, resulting in the formation of substituted benzene. These are the steps which are taking place during the electrophilic substitution reaction of benzene. Let us discuss about the directive influence of functional group in mono-substituted benzene. We have already discussed about this topic in electronic effect in covalent bonds under the heading of mesomeric effect or resonance effect. Once again, let us give a glance over this. The groups like electron donating or the groups like electron withdrawing that may influence the pi electron of benzene ring, whether to pull out of the ring or giving the electron towards the ring. So the electron donating groups are alcohol alkoxy amines or alkyl or secondary amine, such a way we can extend. And these groups, they have a tendency to release their electron towards the benzene ring. Thus that make negative charges at 246 position. The groups are said to be ortho-para directing group. But the electron withdrawing group like NO2, nitro, aldehyde, ketone, carboxylic are present in a benzene ring, where these groups that withdraws the electron from the benzene ring that makes the positive charge at 246 position. So the position 3 and 5 only free from the charges. So the electrophile that may find and attack that third position or the fifth position. Both third and fifth are meta position. So it gives rise to meta isomer and the groups are said to be meta directing group. Let us take phenol. That phenol, it has the oxygen atom, 2 lone pairs of electrons present. But the ring is the more electronegative than oxygen and hence the ring it withdraws its electron towards itself and hence this electron comes out of it. So we have a negative charge over here and 2 more bonds are present. And it starts to delocalize the negative charge which enters over here and this comes out. So we can write. So this bond it comes out. So the negative charge is now at 4th position. Once again it enters into the ring and this negative, the pi electron comes out of that. We are getting the negative charge at 6th position where the pi electrons are present in it. And furthermore we can write one more structure where we will get the phenol and hence the position of the pi bond will be differed. So here and all we have to get a double bond because the pi electron is given to the ring and the finally this electron get into the ring, oxygen withdraws its pi electron, so that makes the position of pi bond like that. So as a result of electron donating effect of OH group, it develops negative charges at 2, 4, 6 position where the electrophile, that is the positively charged one, can attract easily. So these groups are said to be ortho-para directing group. And in the case of nitrobenzene, where the nitrogen is bonded to the 2 oxygen atom which is more electron negative than the nitrogen, and hence one of the pi electron is attracted by the oxygen atom. So a positive charge will be developed, and hence in turn the nitrogen attracts one of the pi electron from the ring, and hence it makes a double bond with it, and as the carbon loses the electron, the second position of carbon gets positive charge, and we have the electrons over here which are now attracting towards the positive charge. So now the positive charge is accumulating at 4th position, and hence this pi electron is attracted by the positive charge. So now positive charge is developed at the 6th position and the pi bonds are such a way. So in all these cases also the nitrogen and carbon has a double bond where this pi bond enters into that and this electron to there. So we will get once again the structure of molecule like this. So as a result of the resonating structure where we are finding the positive charges at the 2nd position, 4th position, 6th position, only these 2 positions are free from charges, but the incoming electrophile that would not attack the positively charged site because of similar charges. So the electrophile that may prefer to attack the 3rd position of the ring, the 3rd or the 5th position is said to be meta position, and hence such substituents are said to be meta directing group. We are at the end of the chapter. The last topic of this chapter is carcinogenity and toxicity. We studied about aromatic compound, and these aromatic compounds are usually present in spices and food items and all. But when number of ring increases in this aromatic system, the carcinogenity and toxicity of aromatic compound also increases. Carcinogenity is nothing but that matter which causes or which induces the cancer cells, that is called carcinogenity. So when number of aromatic ring increases, that may lead to cancer, and such aromatic compounds are having the very high toxic nature. So this is what the carcinogenity and the toxicity of aromatic compound. Okay students, we have completed one more chapter from organic chemistry. Let us see the next session with new chapter and with new topics. Until then, bye bye.